day 2, and this is my lecture 3 for the GAN course. Today I am going to about the synthesis methods that can be used to prepare, to create or to fabricate the nanomaterials. Yesterday you might have seen one of the method that professor taught you about how to fabricate the nanoparticle. Combustion method he has explained you. In the same line, I am going to tell you about the various kind of synthesis method that can be used to prepare the nanoparticle. Yesterday, we have seen the size, shape of nanoparticle, as well as we know about the basic of nanomaterial. So far now, you already understand the basic about nanoscience, nanotechnology, their shape, size, and various types of nanomaterial. Today's topic is about synthesis methods. But to begin with today's lecture, let's have some revision what we learned yesterday. Please see the question carefully and try to answer yourself. Okay? If somebody know the answer, of course, he can give the answer. So please read. There are few questions, 6 to 7 questions. I'm going to display one by one. The first question, which one of the following is an example for semiconducting nanowires? Silicon. Silicon is considered as a semiconductor material. If you see nickel and platinum, these are pure metal, so they are not semiconductor. So here answer is silicon. Yesterday I told you about matter, or their band gap also changes. Depending on the band gap, we have classified the materials as semiconductor, insulator. So if the material is semiconductor, it has certain band gap. If the material is metal, they have small band gap. So the answer is silicon. Who discovered nanotube? So yesterday you have seen nanotube. I have shown you one of the pictures, and in that picture there was carbon nanotube, multi-wall, double wall, and I also told you about the carbon. If you remember, carbon is versatile material. We have seen various allotrope. Carbon nanotube is one of the allotrope of this carbon family, and this carbon nanotube was first discovered by Japanese scientist Sumio Ijima. This carbon nanotube was in the picture until graphene has been discovered. So 1991 to 2005 or 2010, almost 20 years, lots of research has been done on carbon nanotube. And it was, we cannot say replaced by, but most of the researcher has moved their research topic from carbon nanotube to graphene due to the graphene property. However, in some cases, carbon nanotube is equally important. So the answer is Sumio Ijima. Which of the following is an example for electrical property of nanostructures? Which property is a part of electrical property of a nanostructures. Both single melting or from this side, this one, tunneling, both. Which one of the okay, which one of the following is an example of conduction? Okay, so in conduction, what is current means? It is electrical property. So what happened when we talk about electricity, electric current? It's about the movement of electron. Okay, so it jump from one region to another region, valence band to conduction band. So when there is a movement of electron, that is tunneling. It's a kind of movement of electron. So same thing happen in electric current also, but tunneling is a different phenomena. It is related to the electricity. If you heard about quantum tunneling, when electron move, if you apply certain kind of electric field to the material, then electron jump from valence band to conduction band. So depending on how much voltage electric field you are applying. This is the same concept in television we have used. We have electron gun and we apply some electric field, and then electrons are generated and they strike the screen and you can see the image. So the tunneling current. I think yesterday professor might teach you, so most of you already know, but if you remember, there might be sometime confusion about abbreviations. So what is SEM? Sometime we say same. This one, fourth one. Okay. Scanning electron microscope. How to remember it in simple? Because in SEM, electron is used. So you should remember this keyword. Okay. So you will never, because scanning electron microscopy, yesterday professor might taught you about this. So electron is used, it strike on the sample, and then again it was detected by the detector, you can see the image. So the answer is scanning electron microscopy. Sorry. Oh, this one. Which one of the following is an example of zero dimension? Zero. So yesterday we learned dot, two dot connect line, two line connect, two dimensional, two sheet connect, three dimensional. So that way, nanoparticle. Very easy again. Who defined the term nanotechnology? Okay, so Norio Taniguchi. This yesterday we have seen, he was working on the microscopy, electron microscopy, and he's the first person who used this term as a nanotechnology. So the answer is Norio Taniguchi. Which of the following is an example? Sorry, what happened? Okay, is an example of one dimension. Nanorods, line, wires, lines, okay, line, wires, or rods. So it can only extend in one direction, this or this. It cannot extend or increase or expand or grow in another two direction. Only one direction, so it is one dimension. And what is the example? Nanowires, nanorods. Okay. So always remember, one dimensional means something like rods, wire, rope. And two dimensional means sheet like structure, like paper. Just imagine you are holding paper, that is two dimensional. So it is very easy to understand. Particle, zero dimension. Rods, wire, one dimension. Sheet like structure, two dimensional. Cube, spheres, three dimension. So that was the revision of the yesterday's class. Now let's move to the today's topic, how to create the nano particle. Yesterday we have seen various type of shape and size, like three-dimensional structures, two-dimensional structure, one-dimensional and zero-dimensional. How to create, how to fabricate these materials, what are the technique, and whether we can use the bulk material to create two-dimensional, whether we can create one-dimensional using two-dimensional, zero-dimensional using one, and from zero dimension we can create this three-dimensional. Is it possible? Let's see. You want to create a small particle that we call as a nanoparticle. Now, so far there is no machine that you put something big and it come out with a small structure. There is no shrinking machine. Okay, like you put gold bar in certain machine and you can see the powder is coming out in a second. There is no such machine available. Future we don't know, but at this moment there is no shrinking machine. Or you can press it and it become very small. So since shrinking machine is not available, we have to create the nanoparticle in the laboratory using various technique. And this technique is depending on our desire for creating the nanoparticle. What type of nanoparticle we want to create? Each technique has some disadvantage, some advantages, and your application area is important. What kind of nanomaterial you are looking for? According to your desire of creating the nanoparticle, you choose the synthesis methods. So when we think about creating the nanoparticle, we have to create in the laboratory. So those creation of nanoparticle can be done two ways. Again, I think yesterday you might have seen this slide. I'm not going to tell more detail. Yesterday professor already has shown one or two slides, but let's look at quickly. There are two approaches. One is top to down, okay? Like you are on the top floor and you are coming on the down or first floor or ground floor. So that is starting from big, like if you want to make some kind of small statue and there is a big stone, you can carve it and make a small kind of structure. So started with big and end up with the small. So that is top down. Another technique is bottom up. So bottom up, you start from very small particle and then you create a bigger size. Like you might play Lego when you was small. You play with the building block or Lego. Those kind of game, you start with very small pieces and end up with certain structure. So that is bottom up. From zero you start and you create something. So nanomaterial can be synthesized two ways. One way is from larger size to smaller size, top down. And another, you start with very, very small size. It may include chemical reaction starting from atomic level. And then you ends with various kind of nano shaped particle or structures. So that one is bottom to up, from down to up. And this one from top down, top down. You started with bigger size and ends up with the small size particle. So in the top down, usually we use the bulk material. We use the bulk material. Bulk material may be sometime it is few centimeter also, sometime few millimeter also. So bulk material usually bigger, then we convert that big material into powder. Maybe you crush it, you give some kind of mechanical force, or you grind it, or you use certain kind of treatment so that this bigger particle can become smaller. So it can be converted into particle. Again, particle can be crushed or use certain kind of treatment. That treatment might convert this powder size particle into small nanoparticle. So here, once nanoparticle, then also it is possible to create quantum dot like or cluster like structure. Again, give certain kind of treatment to them so that size can be reduced. So this is scale down, okay? Scale down means bigger size, smaller size. And this another approach that we were talking about is starting from bottom and goes up. So this approach of creating nanoparticle is started with the larger size, convert into small size. Mostly they are physical method, mostly. And large scale production is available because you started with the bigger particle. Deposition over large area and large, these are two different things, okay? Large scale production and deposition over large substrate. You can deposit on bigger scale at a time, and large production is also available. In short time, you can create many nano structures. Chemical purification is not required. If the process is physical process, then most of the process don't require any kind of purification because it don't have any kind of impurity. But if the method is chemical, there might be chance that it might have certain kind of impurity. And this method is not cheap because instrument is little bit expensive, broad size distribution. So sometimes size variation might occur. You cannot get the uniform size. So varied particle is the same thing. Control of deposition. You cannot control the deposition properly because these kind of methods can be conducted in certain environment. Require more time for preparation in some physical methods. And bottom up, started from small and you can end up with the nanoparticle. So here you start from the very tiny small particle and ends with the bigger particle on nanoscale. So this process, I think connection is okay. Yeah. The bottom up approach process start with the smaller and ends with the nanoparticle. It's a combination of atom and molecule to make the complex structure. So it starts with the atomic level, okay? atom to atom react together, make a molecule and create the nanostructures. It include both physical as well as chemical. Sometimes one method has physics and chemistry also. So physical and chemical methods are included in the bottom-up approach. Ultrafine nanoparticle is possible because reactions start from atom to atom. So possibility of getting the clean, clear structure, crystalline structure is very high. Controlled deposition is possible, comparatively less expensive because this kind of technique don't need sophisticated equipment. So you can create the nanoparticle easily with low cost materials. Large scale production is difficult because these methods mostly include in the small area, so large production is difficult to create. Chemical purification is required since atom to atom react with each other and make a molecule and nanostructure. So there might be possibility of byproduct or impurity. So you need to clean the product. You need to clean the nanostructure after deposition. So this is the disadvantage and these are the advantages. Vice versa, like you start with the bigger, create the nanoparticle, and from small structure you can still create the nanostructure. So bottom you start with very small and top you start with the very big. So this, what kind of shape and size usually you get from top down and bottom up technique? Mostly thin film, heterostructures, wire rod and quantum dot from top down. You started with the big and ends up, their size and shape is like this. In bottom, nanocrystal, molecular wires, protein, molecule, atom, this kind of possibility of various structures can be created using the bottom up technique. So their size, how about their size? Because we start with millimeter, in some cases centimeter also, and end up with micro or nano also. And here we started with atomic level, okay? Atomic, chemical to chemical react on atomic scale. So you start with, atom is in Armstrong, okay? So it start from Armstrong level and you can see quantum dot or certain kind of molecular structures, molecular wire less than 1 nanometer is possible. So synthesis methods, what kind of methods that comes under the category of top down and bottom up? There are various, but today I will talk mostly about the 8 technique that can be used to create the nanostructures. In top down, ball milling is one of the popular methods. Second is thermal evaporation. Third is laser ablation. Fourth is sputtering. So these are mostly the physical methods and it is called as a top down method. In case of bottom up, chemical vapor deposition, hydrothermal, co-precipitation and sol gel. So chemical vapor deposition is a bottom up technique. Hydrothermal is also bottom up, and co-precipitation, like chemical methods. You took certain kind of chemical, mix it, use the reaction is occur at certain temperature, that is called as co-precipitation. And another is making sol and gel and mix them together, that is sol gel method. Those who are doing the research on synthesis of nanostructures, you might work on one of the technique, or there are other methods like electrochemical method is there, electrodeposition method is there, and there are other several methods you are using to create those nanoparticle. So first method is ball milling. Ball, okay, a certain kind of ball. Milling, like mixing something in certain spherical shape. That is ball milling. Movement, okay. So here, if you look at the pictures, this picture shows how the nanostructure is created. You have certain kind of bulk material, okay, bulk material, and this is the viol, okay, a certain kind of spherical chamber. In that spherical chamber, you are putting the bulk structure, and these red colors are the ball, okay. So this is the bulk material, and these are the ball, and now you rotate that. So what happened? Collision occurs. So this bigger ball hit, and this bulk particle crush in between, and this process happen very fast. You can increase the RPM. Once you increase the RPM, this ball collision occurs frequently, and when the collision occurs frequently, this bulk material crush and their size reduce. Their size is reduced, and finally you can get a certain kind of material. So those material is nanostructure. So basically here, when you move this ball, so ball crush or grind the bulk structure, and when ball is moving, that movement of anything, if you are standing, there is no energy, but when you move, you have certain energy. Similarly, when ball is not moving, it don't have any energy, but as soon as you started to rotate this wheel, particle gets certain kind of energy, that is kinetic energy, and that kinetic energy reduce these bulk material into nanoparticle. Of course, you can also use the ball milling at high temperature, and temperature might affect the synthesis of nanostructures. So at high temperature, the ball interaction and vessel wall, this vessel wall impact severe phase transformation. If the temperature is high, maybe temperature is high means inside this chamber there will be temperature, and when temperature is there, the gas molecule also quickly goes here and there. So collision happen faster. So ball milling means it is crushing or grinding the bulk material, and this crushing and grinding can reduce the size. However, as I told you that when you crush something randomly, this is not uniform. The probability of hitting this red ball, let's say these two red ball hit sometime this one time, this maybe 10 times. So if any red ball hit this blue particle 10 times, it will reduce the size. But if this same color blue has been hit by 5 times, 6 times, its shape will not change as hit by 10 times. So there might be variation in the particle size, because this we cannot control. It is in closed chamber. So this methods is used to create the nanostructures. This method mostly used for metal alloy. This ball is metal ball also, and bulk particle mostly for metal alloy. This kind of method called as ball milling is used. You can see YAG, yttrium, garnet, this kind of phosphorus material, the shape is 50 nanometer, okay? But you can see this is 50 nanometer, okay? 50 nanometer. So some particle is very small, okay? Like this particle is very small, but some particle is very big, okay? This is very small, this one is very small, this is medium size, and this is bigger size. Why there are variation of size? Because of probability of hitting that steel ball to the bulk particle. So what are the various factors that change the formation of nanostructure? Size of ball, size of viol, like chamber, and what kind of ball we are using, smaller, bigger, or mixed kind of ball. Some balls are bigger, some are medium, and some are small. So what kind of size we use? Then total number of ball, how many balls you are using? The probability of hitting increase if you are using more ball. Speed, rotation, RPM, that viol, chamber is moving at what kind of speed, what is the RPM. Amount of powder, bulk material, how much bulk material you took. If the ball is more and material is less, you will get more fine nanostructure. Ball is less, material is high, you will not get the smaller structure. Milling environment, whether you are increasing temperature or doing the reaction at room temperature. And how long? Time. How much time? Whether you are doing this process for 5 minutes, 10 minutes, 30 minutes, or 1 hour. So that can also affect the synthesis. Number of ball, I already explained. If you increase the ball, the probability of hitting the bulk material become high. The collision, number of collision is also increases, and smaller quantity of powder into the air can quickly reduce into the smaller size, and you can get higher efficiency. So advantages of this method is high capacity, long-term maintenance, simplicity in serving, reliability and safety. So simple method, you have just closed chamber, you rotate the chamber, put the ball inside, and you don't need any kind of other equipment. So method is simple, don't need big equipment, a simple equipment is enough. Used to reduce the thickness of stacked material. So sometimes if your intention is to only reduce the size, then this is one of the good technique. If your interest, like you are getting maybe 1 micron size or 500 micron size nanoparticle, you want to reduce the size, then you can put it here and size will automatically reduce after certain time. Disadvantages, the ball mill usually destroy the crystal structure and introduce many defects, heavy and inconvenient. Yesterday I told you that each material has certain crystal structure. Atoms are arranged orderly, that is crystalline structure. But when this ball hit, it has kinetic energy. So when you use your mechanical energy to rub the pencil, you create graphene also. Similarly here, that ball, when it hit, it is possibility that the bulk material might be break at certain maybe atomic scale. Some atom might be gone in the regular arrangement and defect might create it. So chances of creating defect is very high. Grinding consumes lots of energy because of friction, material heating and wear. So when collision occurs, it hit the viol and chances of friction is there. Also, when something is hit, the temperature is automatically become high. Noisy and contamination. If you look at this, it make too much noise because steel ball are there and steel chamber is there. It make lots of noise. And it is heavy and inconvenient also. So it has disadvantages and advantages. Thermal evaporation is very simple technique. The next technique is thermal evaporation. A very simple technique. Thermal. What is thermal? Heat. Evaporation, something evaporate. From one state to another state, it is evaporation. Like if you boil the water, water is converted into gaseous phase. That is evaporation of water. So evaporation of material using certain kind of thermal process. Thermal means heating, annealing, increase the temperature. So increase the temperature to evaporate the material. So what we do in this technique, basically you have certain kind of target material. Any material you put, metal or sometime even alloy, you just put it here in the boat, okay, or crucible. So this one is sometimes ceramic and this one is the target material. So for example, you put aluminum or gold or silver here and this is the crucible. This thermal evaporation occurs at high vacuum, okay, inside the chamber having the high vacuum. As soon as you heat this crucible, thermal means heating, you heat this material, that is your target material, the vapor started to come out from your target material and then they goes in upward direction. Where you have put substrate. It may be silicon, it may be steel, it may be glass substrate. So any substrate you put it here. And then when the evaporation started, this small particle can attach, can adhere, can connect to this substrate. And in this way, you can create thin film. So this is same principle when you see the boiling of water. But this process is performed in the water, in the vacuum. Thermal evaporation create this thin film. Of course, if you want to have better nanocrystal structures or thin film, you can heat this substrate also. Because when you are heating here, it has certain temperature. Certain temperature means if the melting temperature of any target material is 800, so you need 800 degree Celsius here. But distance between this and this, it may be 5 centimeter, it may be 10 centimeter. So if it is 800 here, it will be not 800 here. So if you want to maintain certain temperature, you need additional heater here so that these particle can attach to the substrate. If you don't give the heat to the substrate, then this particle cannot attach easily. In some cases like aluminum or some other metal, it can easily, but the adhesion is not strong. If the substrate temperature is there 100, 200, 300, then adhesion become more strong. To keep the difference between this target material temperature and substrate should be minimum. It should not be high like 800 and room temperature. So since it is a uniform, okay, this evaporation is uniform, they goes smoothly from this target to the substrate, and you can get a continuous deposition of thin film. The process can be affected by various parameters such as temperature, time, how much temperature you are giving to substrate, or how much temperature you are using. For example, I told you target can melt at 8. So how much you are using, 800 or 850 or 900? And distance from source to substrate. So this one target to substrate. How much distance? Whether it is 1 centimeter, 2, 5, 10. So that also decide the quality, okay, adhesion and thickness. It affects the thickness. If substrate is very near, thin film will be more thicker. These are some of the pictures, ACM images rather than picture, ACM images of bismuth sulfide thin film on ITO. So this is various maybe condition they have put, and you can see the uniform homogeneous thin film can be deposited on ITO glass, indium tin oxide. So we already discussed about the factors those can affect. What are the advantages? So advantages, not require any solvent. You just put the target material into the crucible, give the heat, and evaporation started. So you don't need additional solvent. Suitable for material with low melting point. For example, aluminum. Okay, if you want to deposit aluminum, it has low temperature as compared to other noble metal. So you can get the deposition in quick time. Low cost method among PVD, physical vapor deposition. This is physical vapor deposition. So this is low cost. Why? It need vacuum chamber and heater. Okay, only two things it need. So relatively cheap, relatively cheap. Disadvantages, alloy and metal combination are difficult to deposit. Why? Because if you want to deposit silver and gold, so you put silver and gold, because their melting point is different. It is not possible that they mix up and they will go. It is not going to happen. So that is the disadvantages, that at a time you cannot make alloy, nanostructure alloy, or some metal combination because of different melting point. Only process parameter, control to fill, and quality. So process parameter is sometimes difficult to control the quality of the film. Source material could be poor. Sometimes, even though we say melting point of certain material is low and we give the heat, it cannot show the good performance. Evaporation cannot happen as we expected. So that is the material's property. So sometimes deposition is not good. Even the target material has crossed the melting point temperature. Next technique is laser ablation. Laser ablation is the technique that I am also working on. From last 10 years, I am using this technique to create the nanostructure. This technique is physical technique. Although it use liquid, okay, although it use liquid. In the last technique, we have seen you have target material and you give the heat. That is thermal. Here we use laser. We use laser. So this laser is irradiated on the target material. On the target material. So laser ablation uses this laser, pulse laser, okay, and that pulse laser is irradiated or it goes toward the target material with the help of lens and mirror. So laser has only one direction. If you want to change the direction, you need mirror and lens, okay, mirror to change the beam direction and lens to control the diameter of laser, okay. So mirror is required to change the direction. If you don't have mirror, laser is a monochromator source, so it will move into one direction. Then this laser is change the direction using the mirror and then focus onto the target material. We can use various target material like metal or ceramic also, or even polymer. What happened during this technique is very interesting. This is top down technique. Look at this target material, very big, and laser is coming on the surface of this target material. So what happened so that this nano structure is created? So nanostructure is created. Similar kind of incidents happen in thermal evaporation. In thermal evaporation, the particle started to evaporate from the target material, okay, in the vacuum medium. Here, liquid medium. And once laser hit the target material, nanoparticle is created. How? You can see here. Laser energy is used to remove the material from target. This is target material, okay, and bulk material, maybe 1 centimeter by 1 centimeter or 2 centimeter by 2 centimeter. Thickness maybe 0.5 millimeter or 1 millimeter. The high power laser pulse hit the surface of target, leading to melting, evaporation, ionization of material. When laser hit the substrate, the possibility of melting target material, evaporation or ionization of material can occur. Why melting? Because if the bulk material has low melting point, the plasma is created here, okay. The heat, a certain kind of heat is created. That heat, if that heat is more, then melting might occur. If heat is not more than the melting point, then evaporation will occur. So evaporation means particles started to get away from the surface, or sometime ionization might occur because of plasma. This is solid material. Target is solid material. Outside is a liquid. So liquid solid interaction or interface is there. And at that interface, plasma is created. Plasma is created. So due to this plasma, ionization or evaporation can occur. This is pulse laser deposition. Pulse laser. Pulse means 10 nanosecond pulse. Every 10 nanosecond, one pulse is going on. So that phenomena occurs in 10 nanosecond. Okay. So this plasma is created in 10 vanish. 10 nanosecond created, vanish. But this is continuous process. Okay. Continuous process. So this heat create shock wave. Like if there is a river and you throw the stone. When you throw the stone, such kind of circular waves are created. Same pattern you can observe in the laser ablation. When this laser is continuously heat and this heat removes some kind of particle, this area is affected, and since this area is affected with the laser energy, the shock wave is created. The bigger the area, bigger the shock wave. This is nanosecond laser. Okay. Nanosecond, why it is called as nanosecond? Because it has nanosecond pulse. This is continuous laser. Okay. When I am starting, this is continuous laser with less energy, so my hand is not affecting. But we are using nanosecond laser with certain energy, let's say 60 millijoule or 60 milliwatt, 600 milliwatt. So here the laser, 10 nanosecond laser like this, every 10 nanosecond one pulse is going or created or irradiated to the substrate. Yes. Okay, okay. This one. Laser is monochromator source, okay? So when I put, it cannot change the direction itself. I want to put this laser towards you, I cannot. But if I put the mirror, so mirror reflect, okay? It has a concave mirror and that can move the direction of laser. Yeah, possible, possible. But I don't have the picture. Usually laser equipment is like this, okay? And it is big, okay? You cannot put the big laser like this, okay? So laser equipment sometime like this, okay? And we are putting on the table. And we put this beaker somewhere here. So laser is created like this way. And now we want to move this laser here because beaker is here. So that is one of the. If laser is very small, then we can put like this. Our aim is to put the laser vertical, okay? Another way of creating the nanostructure is you put laser like this, okay? Simply like this. There are two ways you can create the nanostructure. One way, you use target material in the form of solid. Another, you just simply put the powder. The powder size is few micrometer, let's say 1 micrometer or 10 micrometer. So you just mix the powder, and you can also use the stirring. And in that case, you just put this laser horizontally, okay? This laser is vertically, okay? We are putting vertically. Another way, you just simply put your beaker here, that's it. So like this, you can put, it will be created, okay? So there are two ways. One is irradiate with horizontal direction like this. Another is change the direction of laser and make it vertical. So if the laser is nanosecond, more heat affected area. But if laser is femtosecond, imagine, okay, nano and femto. Nano means 10 to the power 9. Femto is more small, okay. So femto affect less area and less shock wave. So this is the difference. This is the difference. If the area is very small, then you can get more smaller particle. So basically what we do, earlier was, this is vertical laser ablation, vertical. Another is horizontal, like this, okay. We are just took the water, and in that water we put the powder, any powder, you whatever you want. For example, SNO2, WS2, even RGO, any powder, you just put it, close the glass beaker with the lid, and then use this laser horizontal. Of course, you use here magnetic stirrer so that powder should disperse uniformly. and after certain time you can get the nanostructure. After certain time, maybe in some cases it is 5 minutes, in some cases it may be 10 minutes, 15 or even 20 or 2 hour. We are using 532 nanometer wavelength, okay, green. This is green, okay, such kind of laser we use. This is the example, indium selenide. Indium selenide bulk powder we put into the water, and this is the specification of laser, Nd:YAG laser with 500 nanometer and 620 milliwatt power. After 5 minutes, this bulk material, so bulk material means it has a size up to 1 micron, 2 micron or even 3 micron. That bulk material is in the form of sheet, okay, like paper. When you deposit this for 5 minutes or irradiate laser with 5 minutes, it started to change its shape into the rod like shape, and there are some spherical particles. After 10 minutes, rod again vanishes, it becomes spherical and few rods. After 15 minutes, the rod started to convert into the cube, and after 20 minutes, the uneven shape cube become even shape nanocube. Within 20 minutes, you can get the formation of nanocube. So this was the paper published in 2021. This way you can see how the size reduce, You started with the bulk material. Earlier was ACM image, this is TM. This one is the bulk material you put here, okay? And this is sheet, like paper sheet, one by one top, like that. But this sheet, 2-dimensional, is convert into 3-dimensional nanocube. So these sheet align themselves and change their shape into cube. Yesterday I told you, if you have high surface area, the more reactive area is available for reaction. So here more area is available, and since more area is available, it can be used for a certain kind of application. In our case, we have used it for field emission application and photocatalysis also. We characterize this material and see whether indium selenide was indium selenide or not. So here is bulk material, then this is the nano cube, and structure is intact after TM and XPS. Next experiment we done, we took powder, this time horizontal laser ablation powder, uneven powder. We crush it, okay, for 2 hours and make it fine powder, put into the water and do the laser ablation for 2 hours, and you can see black color powder change into yellow color. Yesterday in my first lecture I show you gold bulk is yellow color, but you can see different kind of color for the gold. Same thing is happening here. If you see the bismuth selenide powder, bulk powder, it is black color, but after 2 hours it become yellow. So when it become yellow, it will show different property, definitely band gap changes, conductivity effect. So bismuth sulfide is also kind of topological insulator, but it convert into semiconductor, and this material can be used for FET application. So this is the after crushing, okay, after crushing, these are sheet like structures, then it convert into rod, convert into nanocube, convert into rod also. So there are two ways this growth mechanism occurs. One way, when you have large bulk particle, when laser is irradiated on this bulk particle, this sheet-like structure breaks into several small pieces. Okay, small pieces. Again laser collide again into small pieces, cluster-like formation, and then creation of nanopart. This is one of the possibility of formation of nanostructure. Like you can get small spherical nanostructure. Another is this bulk cannot crush or divided into small particle, but it like having small sheet after laser striking. It convert into small sheet. Only few area is affected. This time only half. Another laser pulse come, then again this area is break and it fragmented. Like if you have paper, you make it in several pieces. You make it half, then again quarter, and then 8 pieces. So same thing can be happen as laser irradiate on this sheet, and you can get sheet-like structure. Sheet-like structure. So when you have sheet-like structure, it can align itself, and certain kind of shape can be possible to transform the two-dimensional nanostructure into rods, into nanocube, or into different kind of structures. So this laser ablation can be controlled on various parameter. When you change this parameter, fluence, wavelength, repetition rate, pulse duration, transmission or light absorption, how much energy, how much time, how much fluence, what kind of laser you are using, those all parameter can control the synthesis. Even the chemical composition of liquid can affect the laser ablation. In our case, we are using water. Sometimes we use methanol, ethanol, or combination of water and ethanol, 30% ethanol, 70% water. Sometimes we put the bulk material into water, but it cannot disperse. If it cannot disperse, then we need to use a certain organic solvent like ethanol or methanol. Then it can disperse and uniform formation of nanostructure is possible. Since this synthesis carried out in pure environment, in liquid environment, pure nanoparticle can be formed, low loss of energy. All energy is utilized because energy is given in the form of pulse. Less waste and eco-friendly. So byproduct is not created. That's why no wastage of material, and it is relatively low cost method except the price of laser. There are some disadvantages. Lots of energy we use because to on the laser you need high power supply, unable to produce nanoparticle on industrial scale. Since this pulse is very small, it cannot create the large area deposition. Efficiency of ablation decreases with longer ablation time. If you put the laser for longer time, the efficiency decrease. Like I have shown you indium selenide. After 5 minutes, rod. 10 minutes, rod plus spherical. 15 minutes, uneven cube. 20 minutes, cube. But if you go after 20 minutes, that cube started to again convert into ball. Okay? So longer laser time is not good for some structures. The fourth one is sputtering. Sputtering is also popular technique to create the nanostructure. In this case, it is very similar to thermal evaporation. But here also you use the target material. In thermal, you literally give heat to the substrate. Here, RF sputtering or magnetic sputtering. Those source of energy is RF sputtering here instead of thermal heating. Then RF sputtering heat the target material, and again similar kind of phenomenon occurs, and after evaporation you can get the thin film on the substrate. Because when RF sputtering is used, high energy ion is created. Thermal energy cannot create the ion, but this sputtering create the ion and it strike on the substrate. Once this substrate is strike with the high energy ion, they try to go toward the substrate, and in this way thin film can be deposited. It require various kind of RF source to activate this target element or target material, and this process is created into the vacuum condition. Once we use this RF sputtering, it has use in the vacuum, and electric potential must be applied between two electrodes. Now if you look at this, in thermal evaporation you simply heat, but here RF sputtering. So electrode is used like positive, negative, and due to RF this sputtering, the electric charge, electric field is between this anode and cathode. So that created ion is attracted toward the substrate or move this particle toward the substrate. Now this evaporation is in gaseous form because of vacuum. So this particle move toward the substrate, and in laser ablation plasma is created. Here also plasma is created. Why plasma is created? Because you apply electric field between anode and cathode. That's why charge particle is created. So once charge particle is created, they attract towards, so this is cathode, this is anode. So oppositely charged particle attract to each other. Sputtering can give you uniform deposition. Also, sputtering is used for low nanometer scale. Like if you want 1 nanometer coating, then sputtering is very good. 2 nanometer coating of certain material, AG, AU, you can use sputtering, and uniform deposition. Look at this, okay? These are the example like AG, okay? 1 nanometer, okay? 6 nanometer, 8 nanometer. So 1 nanometer is uniformly deposit. These are the factors which affect the synthesis: temperature, time, and layer of thickness that affect the deposition. Target to substrate angle, bombarding particle mass and energy, argon ions in vacuum, substrate temperature. So when you apply electric field, substrate need to be heated so that uniform deposition can occur. These are the advantages. It can work at low temperature. Like in thermal evaporation, high temperature is required. High temperature means melting point, then and then substrate will evaporate. Here low temperature is okay because plasma is created due to the electric field. Large area deposition with uniformity. You can put large silicon sample like 6-inch vapor you can put, and it is possible to create the large area deposition. Elements, alloy, compounds can be deposited. So in thermal evaporation, we cannot create alloy nanostructures. Disadvantages, deposition rate is very low. So sometimes 1 hour deposition only few nanometer. So this is like time consuming process. However, uniform. Target convert most of the energy into heat. You are applying electric field. So most of the energy is given to the target material. Expensive equipment and need more time. We have 20 minutes and I will try to cover 4 techniques, but this technique, one of the technique is very important, chemical vapor deposition for bottom up. I will skip this slide. Chemical vapor deposition. Chemical vapor deposition. Chemical means use chemical. Vapor means vapor are created. Deposition means deposit the substrate. So this is the simple meaning. In this case, you took 2 gases. One gas is precursor, another is non-reactive gases like argon gas. Sometimes you can use reactive gases also. Here what happened, there are heater and this is gas in and gas out in the vacuum. So this CVD technique use gases. It is bottom up. I told you that in bottom up the reaction started at atomic scale. Okay, so when you are using the gas, now gas molecule. In the gas, what is gas? Gas means gas molecule and they can move here and there. So matter of state, liquid, solid, gas, plasma. So in case of gas, these gas molecules are free molecule. They are not attached to each other. So this gas molecule come here and they get heat, and when they get the heat, they break into the spaces, and these spaces, reactive spaces, only deposit on the substrate. Remaining spaces can come out through these gases out. So I will explain this, how the nucleation happens in CVD technique. What happened? Basically, nucleation and growth is very important. I just show you that how indium selenide nanocube is formed by laser ablation. Similarly, how nanostructure is formed. Whether it is liquid or gas, initially there should be some kind of nucleation. Like if you want to have the building, you need foundation. Then you can build the big structure. Similarly, to create the nanostructure, you need some kind of nucleation, some site that can grow the nanoparticle, some base. So that is nucleation. And then that nucleation start the growth of nanostructure. How it happen? In case of CVD, let's see. When you put the gas, okay, this is argon gas and this is, let's say, hydrogen gas or methane gas. If you put this methane gas, methane means CH4. Now, C means carbon, H means hydrogen. So this carbon and hydrogen spaces will come into the chamber. Now, chamber has certain temperature, high temperature. This high temperature will break CH4 into carbon and hydrogen. Your target is to deposit carbon. then you don't need hydrogen. But this hydrogen you don't want. The argon gas will push this hydrogen molecule to the gases out or exit. Okay. Remaining C, that is carbon, will push toward the substrate, So this way, initially what happened, the spaces can break due to the temperature, and like MCl2 and H2 means that non-reactive or reactive gas. Argon you can take also. When this carbon and hydrogen species is decompose, separated, break down, only reactive species attract or goes toward the heater which has a substrate holder, and carbon can be deposited here. Remaining particle can goes out. When you heat this chamber, this, let's say, green and yellow molecule means it has two atoms, and you push some kind of hydrogen or argon also to transport this molecule, to push. And after a certain time, this movement continue. One certain amount of gas come, and then again you have heat, and this argon or hydrogen is transporting these species toward the substrate, okay, like this. Now, uneven or unwanted or impurity or byproduct gas will come out from the exit, like CH2 means carbon and hydrogen. And if you use another hydrogen gas, so that C will break and H4 will break, but that H4 will react with hydrogen, and when this, here is CH4, okay, CH4, and this is hydrogen. Now this hydrogen will react with this hydrogen like this, and then this will react, and then it will throw outside the chamber. Only C will remain on the substrate. So this way there are many processes, but due to time I am not going to explain you. Only remember that in CVD methods, breaking of material happen. So any material, any gases, usually it is in the form of carbon and hydrogen, and that carbon hydrogen species break due to the temperature. Remaining unwanted hydrogen like species react with argon or maybe hydrogen, and they can throw out from the chamber. So these are some of the chemical reaction occurs in the CVD method, like pyrolysis, like separation of species, oxidation, sometimes hydrogen to hydrogen react, sometimes hydrogen react with sulfur also, and H2O gas can release, sometimes chlorine gas can release, depending on what kind of gas you use. And these are some of the example of nanostructures. What kind of factors that affect the deposition, like pressure, gas flow, time, precursors of nature, what kind of gas you are using, and temperature. Large area fabrication is possible, uniform coating can be done, homogeneous structure can be obtained, growth rate can easily regulated. We can control the growth rate because when we use the CVD, we know the growth rate. After 1 hour, 5 nanometer happen. After 2 hours, certain nanometer can be seen. So we can control the growth of nanostructure. and it has reasonable processing cost. It's not like high cost technique. Only gases is expensive, other thing is not so much expensive. It do have some kind of disadvantage, like gases sometimes explosive, like H2 gas is reactive highly explosive gas, or sometimes silane is also used to create amorphous silicon, and it has some limitation like high temperature. Sometimes poisonous gases can create the hazardous gases like chlorine or even sulfur. Hydrothermal is a pure chemical methods. In hydrothermal, what you do, basically you took two solution, you mix it together, two different kind of chemical, you mix it and put into the autoclave at certain temperature. So here you have precursor solution. Precursor solution means you have A solution, B solution, you mix it together and then transfer into the autoclave. Autoclave means steel chamber, okay? Steel chamber, and it is closed chamber. Then you put this chamber for at certain temperature, let's say 180 or 200 degree, and after certain time, after certain time nanostructure can be created. Then this nanostructure is in liquid form. You can remove the water content and get the powder. You can dry this solution and get the powder. That is hydrothermal. This is very simple technique. You just need one steel small chamber. You put into the furnace for heat treatment, wait for certain time, 8 hour, 10 hour, 12 hour, 24 hour, and then you can get the nanostructure with different size and shape. This is very popular technique because of two reasons. One, it is low cost. Another, it is very simple technique. Once you mix two chemical, put into autoclave, just transform this autoclave to the furnace and done. Of course, after this, you have to dry this solution using vacuum dry. And these are some of the structure. You can see how this structure has been got. By the way, these structures are three-dimensional structure. Okay, yesterday we have seen such kind of structure is three-dimensional structure. It can grow in three direction. Okay, so this is three-dimensional structures. These are the parameters that affect the technique. Mostly high temperature pressure, because autoclave is closed environment, reaction time and solvent. What kind of solvent? Whether it is water, whether it is ethanol, whether it is a mix of ethanol water, what kind of organic solvent you are taking. Advantages: precise control of size of a nanoparticle, low melting point, high vapor pressure, tendency toward the pyrolysis will be obtained. These are the advantage. You can get the nanostructure at very low temperature, like 150, 180, 200. In thermal evaporation, temperature is in 1000. Melting point of, in other technique, even HFCVD or CVD, temperature is very high, or sputtering, temperature is very high. Comparatively, here temperature is very low. Disadvantages: crystal growth information cannot be observed directly. We cannot see what happened. We cannot predict how the flower is generated. We have to guess, we have to use our knowledge and then predict the growth mechanism. Expensive autoclave, it is still difficult to control. Sometimes the formation of nanoparticle is difficult to control if we don't know how this particle is transformed. Co-precipitation is a chemical technique, is a simple chemical technique. What is the difference between hydrothermal and co-precipitation? In case of co-precipitation, you just add to solution and mix it, either stir or just aging, and you can wash the solution and get the nanoparticle. In case of hydrothermal, hydro, water, thermal, heat. There is no thermal. So hydrothermal means water and heat. Precipitation means only mixing and stirring or aging, you can get the nanostructure. These are some of the pictures. These are the parameters that affect the formation of nanostructure. I will not read, we are coming to the close of this talk, so I will not read. You will get the slide. And sol gel is the last method that I want to tell you for a few minutes. Sol gel means sol and gel. Sol means solution. Gel, you know the gel. So here sol and gel is created separately, sol and gel. Sol and gel. Okay. So this, you took certain kind of solution, and with the hydrolysis you can create the solution, and after that it transforms into gel, and this gel may be processed for thermal drying or different kind of superficial drying or freeze drying. So high temperature or low temperature. Thermal means high temperature, freeze means low temperature, and then you can create the nanostructures. So basically sol gel means it kind of colloidal solution which form into the liquid having the size up to 100 nanometer. The gel is the solid micromolecule immersed in a solvent. So gel is look like solid, but it is called as micromolecular size. And solution means it's pure liquid. So you mix together and give certain kind of pre-treatment to make the nanostructure. These are the pictures. Sol gel method also produce uniform structure. These are the advantages. When you are using the water and you use some kind of pre-treatment, in that case pH is very important parameter, then speed, stirring time, and temperature, time for reaction can affect the structure quality, porosity, and other factors. Solvent, precursor are very important parameter. Texture and surface quality of material is controlled very well. Desired nanoparticle with correct crystal size can be obtained. Advantages, it's very simple technique because you create solution and then gel and give the certain kind of post-treatment. Uniform, highly pure structure can be created. Low temperature allow introduction of modest amount of dopant into sol that is equally spread into final product. So sol and gel, you can choose how much you can mix them together. Disadvantages, long reaction time. So reaction time sometimes 24 hours or more also. Use organic chemical might cause health risk. Some of the organic like H2O2, okay, peroxide, if you are using for zinc oxide, so that kind of chemical is might be risk for your health. Purification is required to get the nano. So after chemical, any chemical deposition, chances of impurity is very high. You need to clean the nanostructure. So today, with this, I have shown you the synthesis method, 4 method of bottom to down, and another, top to down and bottom to up. So most of the technique that was seen earlier in first part, that was physical technique, and bottom to up was chemical technique. Total 8 technique we have covered. And you might understand now what kind of structure can be created. So what is your desire? What kind of nanostructure you want to deposit? 2-dimensional, 3-dimensional, rod, particle, uniform, 1 nanometer, thin film, coating, liquid form, dried. You can choose any one technique and deposit those material. So with this, I will stop here, and if you have any question, please ask question. Thank you very much. It's almost 12 o'clock. Do you have any question? Yes? Nano scale material too? Nanoscale to picoscale. Yeah, I have told you that when you are going from top to bottom, you need certain kind of treatment, like whether you are grinding, you are crushing, or you are giving certain kind of energy to cut the particle. If you want to go towards the more deeper scale, like picoscale, for example, if you want to use the laser. So laser means what? It remove and cut the material on the surface. So possibility, if your surface is in nano size, and if you put the laser on it, irradiate the laser, it will convert that into pico also. Okay, but to convert into the pico, you need very fine laser, very fine laser. Diameter should be very fine, like less than maybe 0.1 micrometer, so that reaction should occur in small area. If the beam is very big, it will affect large area. So small particle will not generate it. In case of nano, large plasma is created. In case of femto, small area is. So femto, the size is 5 nanometer. If you want to go more deeper, you need another octo laser, because one of the technique, or if you process it like grinding, ball milling is also one of the technique. You need to give certain kind of treatment. It may be crushing or something to reduce the size. Okay. Okay, please. Yeah, without they are gravity free, not gravity free. You cannot push, like if the particle is here in the room temperature, they will not go themselves up. You need to give some kind of energy to push. Okay, otherwise they will just stay on the surface. Air, yeah, if they are light gas molecule, okay, they will be, if their densities, they will be in the air. Okay, so like fog. Okay, why fog is? Because their densities, so they are just laying here, and when they become bigger, so they come down. Any other question? If no question, then maybe we can take a break for, I think, half hour. 20 minutes. Okay, okay, 20 minutes. 11:25. Okay, okay, okay. Thank you.